Hi guys, so I'm Vincent Badwa from BSEC3 and this video will be about discussing the final performance or exam for Electronics 3. So I have here a project hanging, which means handling automation nexus for gated and indoor located noxious air. So my inspiration for making this project is that whenever I do my own private projects, I actually do a lot of soldering and due to the limited space in my room, uh, oftentimes there is always a buildup of the smokes coming up from the soldering iron or the soldering gun, and because of that, I wanted to create a system where there will be an automatic system that will variably that will change the speed of exhaust, even active exhaust, and make an alarm system as well as just basically I can control the airstream within the confines of my room. So basically, it's like an automated aerobic system for production-based environments. It does not necessarily have to be a room. If you have like big enough rooms, such as what they call this, the factories that produces also amount of huge amounts of dangerous air, uh, we can also use this system. So okay, let's start. We have here our detection system. It uses the LM358N, an operational amplifier in comparator mode. So here I have a voltage divider connected to the inverting input, and I also have a reference voltage connected to the uh, inverting input. So basically, what will happen is that if the non-inverting input, which is the 5 volts, is higher than our control here, so it's like going to be if 5 volts is greater than 4 volts, then it will start going to the positive rail, which will be our VCC here of 5 volts. So in the current configuration of 30% of 5 volts, I think this is not conductive when I took this screenshot, but we will be explaining that in the simulation later. So anyway, so once we have a 5 volt signal here, so by the way, the variable resistor here is our sensor. If it's a type of like photoresistor or an LDR, but it's the type of LDR that reduces its resistance in the detection of light. So it can go up to like something around near 300 or maybe 500 ohms, and in that state, VCC here, the voltage across this point should be around greater than 4 volts. Well, in any case, we can also adjust this. It's basically just a simple threshold. So, let's move on to the circuit. The output of the operational amplifier is going through the optocoupler. The purpose of this optocoupler is to control the triac here, as well as others, but we'll discuss first the triac. So here, the output of the operational amplifier will trigger the LED inside the optocoupler, which in turn will power this triac. Now, this triac is configured in a what we call the phase controller. The reason I use a triac here, and then it's just this triac here is just for controlling when the 220 volts load. By the way, this is the load. I forgot to rename. This will be the load, and this is just for the trigger of the supply itself. And after this, the phase controller is here. Here is a diac, and here is a triac. Because I want to control AC motors. For example, the purpose of the AC motor, the reason I want AC motors is because say we have a facility right here, and let's see that. Uh, okay. So for example, this is like a fan. Yeah, that's a fan, and this is another fan. So let's say that we want to move. Let's say someone is doing something here, and then and as time goes on, for example, soldering, there is a time that there is so much accumulant air, dangerous air that it starts to get unhealthy. So I want to be able to control that whenever that point is, or whenever that unhealthy point is present, that these fans will activate. However, if the room is very big, let's say something of the size of like a warehouse, it will not be that power efficient if we just put the fan in in max settings, because it will consume a lot of power. So I want to create a phase controller as well, so that when if there is just a little amount of, little but still pretty dangerous amount of dangerous air, and will only activate at a certain phase angle, and then excuse me, and then if there is a very dangerous amount, then this fan will be powering much more powerful. So that's that, and that's the purpose of the AC motors. Next, here we have a simple buzzer. Connected to the output of this optocoupler is another optocoupler connected to the connected to a SCR latch buzzer. So this SCR will conduct in the presence as well of the first operation amplifier right here, because it is connected to the same optocoupler, so that whenever the system detected that oh no, the temperature is very bad, it will sound a buzzer. So it's basically like an alarm system. Yeah, and this whole part is basically just the alarm system for the system. Next, here we have the last component, which will be our oscillator circuit. Now, there is a lot of purpose for an oscillator circuit. We have VCOs, or the VCO with the voltage controlled oscillators, and we have the stepper motors. We have the what do you call this? The microcontroller inputs. But in general, the one we used here is just a simple pulse generator. So it's like the output will be like this. Oh, it's not straight. So it's like the output will just be like this. And the reason for these spikes is that we can actually feed this into a counter, a digital counter, for example, and it will count how many times this is present. And from how many times it reads that value, we can say how strong the, or I mean, how dangerous the levels really are. But in this case, I'm just using a simple resistor to represent that actuator. We also have here another sensor. So the reason we have another sensor here is that actually it says air quality, but I we can actually replace this with any other sensor. And the reason for this is we can actually change the frequency. We can change the frequency of this oscillator circuit based on that sensor. So that, for example, if we want a high frequency trigger, I mean a high frequency that we have designed in the future, for example, something that would respond to a 1 kilohertz frequency, or even a 10 hertz, or even, if possible, 1 hertz, then for example, something like the CD4017 IC, which is just like which is what they call this, a Johnson counter, which is, or we can configure that to be an LED follower, where we can take the input of a pulse signal, for example. So with that impulse signal, so for example, we are using 10 hertz, then here we have an LED. Let's just assume that all of these are LEDs. So we can see visually that the frequency increases. So like for example, this is red, this is blue, and alternating. So the higher the frequency, we can see that uh, it is more dangerous, because the sensor changes its output. Therefore, with the changes in the sensor value, we can also detect then the, if that's a sensor, we can change the frequency of the RC filter, sorry, for the RC oscillation provided here will also change. So that's the main gist of the circuit. However, in this case, I simply use a simple resistor here. But in reality, we can use any other actuators that will respond to just a simple pulse like that. Simple pulse, similar to the output of a differentiator. So let's check it working. So here's the circuit in multisim. So as we can see, let's try running the simulation. Right now, as we can see, the optocouplers are turned off. Because the reason for that is because our configuration here is that the threshold is actually at 4 volts. So if we want to trigger this, we have to increase the voltage at this point to be higher than 4 volts. Right now it's lower. So it's railed to ground level. It's either I can lower this, for example at 3 volts. As you can see, the optocoupler lit up and the buzzer also sounded. Uh, or we can also just simply adjust this one because this is actually our sensor. So let's actually do that. So let's turn it off for now. There we go. So the voltage right now is 2.94 volts and our reference is at 3 volts. Therefore, the optocouplers are down. But if we lower the resistance up to the point where it's higher, we can see that the optocoupler is now powered on. Now, with the optocoupler powered on, the AC here is now finally conducting, and with that, it's actually doing the phase control now. So let's check the output of the phase controller here in design 2, where I plug in so many meters. Oh, actually, uh, here we can see the output of the comparator. So let's wait. Oh, not this one. Wait, it's set to 200 volts. Wait, is this? Yeah, it's this one. Okay, so right now it should be low because here we have 2.5 volts and our reference voltage is at 4. So if I actually 4 volts is so high. Wait, let me change it to 3. So now let's try making the value a bit higher. So as you can see, there is a spike here, and that's the activation part that I was talking about. Next, let's go to the phase controller. So the phase controller here looks like this. The buzz that you are hearing is basically is the buzzer that I'm talking about. So here we can see that the here in terms of RMS. Oh, I'm sorry. Here, so we can see that the red line is our source, and then the green is the phase controlled one. Right now we have a 150 volts, but if we change the value of our potentiometer here, as you can see, we reached the non-conducting state, so it went completely down. So let's try reducing to this point, and let's wait. So it's now 180 volts. We can reduce it more. It's now 186, 189. Basically, as I go lower here, the higher the voltage we will be getting. So you can see we are now at 198 volts. So this is like, so you can see that for example, we're using a lamp right now, but if this was a motor, then the speed or the RPM of the motor will change with the voltage right here. And that's the controller that I was talking about. And here, it's just a simple buzzer. It's not like, it's just a simple buzzer. It just buzz. So it just makes a sound. Preferably, we can make this a bit stronger. Because after all, it's an alarm system. But with the high frequency around 1000 hertz or even 4000 hertz, honestly, the buzzer is, it's like the sound of a very annoying, what do you call this? The fire alarm system that we hear in room 103 Smart Lab whenever the fire alarm system is on. So it's pretty loud. And lastly, we can check the output of our pulse generation. So this is just a simple UGT slash PUT circuit taught in our Elecs tree. So here I'm taking the output in this capacitor, which is just the relaxation oscillator, and the output that we have is actually here. So we can see actually the optocoupler is spiking. For example, there, it's spiked there. So every spike is denoted here. That's like we can see the impulse, and that is a type of data that we can use. It's either for actually a lot of things. We can use that as a controller for BWM. We can also use that as an input again for a microcontroller for it to trigger something. For example, like an SMS message, an email message. But since this is purely analog, I have again left with just a simple resistor. So overall, what does the system do? It just again let me just take a screenshot here. And oops, sorry. So what it just basically do is that we have here one sensor. We can actually convert this instead of a potentiometer into a sensor as well, so that actually this is what I was referring to. This sensor and this sensor is like basically the same, so that when it detects a higher amount of dangerous air, it will actually change its resistance, and therefore it's basically a resistive sensor, and therefore change the phase control uh, completely by itself. And then here we have our wait, let me just encircle that. And this is an actuator, and then this is our last. That's not necessarily last sensor, but this is another sensor that basically this is a capacitive type of sensor where it changes its capacitance based on the data that it has. And then lastly, we have here, which is another output for our impulse function. Okay, so in overall, we have those sensors, and this is the main sensor that will trigger everything. We can do a much more complicated approach by using more sensors, but give it if it what do you call this? If we use much more sensor, then our data is going to be much more accurate. But since this is just a demonstration, I have just used one here, but we can expand here if you wanted to. So we have here a comparator circuit, and that comparator circuit is just simply gonna say if it's on or off for the system, and if it's on, then trigger everything, everything in this optocoupler range. So it will trigger our 220 volts, which can be our AC motor. So this is an AC motor, and here we have a DC buzzer, which AC motor is for regulation. The DC buzzer is for alarm, and we have the impulse function for miscellaneous for microcontrollers and other actuators that can use, or even the what I said, CD4017, just the lead chaser follower. So that's all for this video. So thank you for watching.